Alright, so in this video, we will be talking about what is enthalpy, right? What is enthalpy? And to answer this question, let's get a glimpse of what is internal energy. What is internal energy? Alright, so that video noted by you. So suppose I have a tank, a tank or a pond. Let's say it's a pond of unknown depth. So I don't know how much water is there in the pond, right? I don't know how much water is there. I don't know how much water is there in the pond, right? But what I know is how much water is getting into the pond or how much is going out. So what can I calculate is net gain or loss of water. This is what I can calculate from the information I have, right? And same is the case with the internal energy. So your internal energy uh, for an ideal gas is the sum of all kinetic energy of the molecules. And if you have a container like this and you add up the Ke of all the molecules inside this container, you will get your internal energy U, right? um, but actually definitely it's not the like best measure of it, because you don't have ideal gas in real life. I don't have any ideal gas in real life. So what I do is um, so defining internal energy for a real gas, I have to consider both kinetic energy and potential energy of the system, right? Of the all gases, right? All sort of energies, I have to sum them up. Now there are infinite, like not infinitely many, but there are a lot of particles inside a box. So it's really a headache for me to actually go and calculate what is the internal energy of the system, right? Like definitely we do have ways of actually calculating internal energy of a system in a way, but that is something we deal with in the kinetic theory of gases, which is not the part of like chemistry, which is a part of more sort of physics. But let's just view the picture from a chemist's eyes. So how I define my internal energy, because for now I'm talking about the time when we don't have that much knowledge into the like we didn't have the Boltzmann and everyone who did their work on kinetic theory of gases to come up with a molecular picture of the gas and to build up everything in terms of molecules. So for now we are actually dealing with the bulk property. So if I am talking about in a bulk, so my internal energy, my change in internal energy, because I told you I don't know how much internal energy a system have, because there are so many particles in a box. So I define my delta U as delta Q minus of W. So what it means is that if this is my box and say the state, like I mean that initially you have some U1 internal energy and you add some heat delta Q to it, and the system does some work like W outside, and delta Q is not equal to W, right? So obviously the energy has to be like, there has to be there has to be conservation of energy, right? There has to be conservation of energy. So you need to introduce some factor, there has to be some change in the internal energy. Only then the law of like the law of conservation of energy can be held, and it can't be broken. So obviously you have to define so you have to say that your system has reached to some second state U2. So when I say second state U2, it means that the kinetic energy plus potential energy of the all particles has increased by some value or decreased by some value depending on the difference between the delta Q and W, right? So here is your change in internal energy, which can be defined as delta Q minus of W, right? All right. Now there is also one more way of defining the my change in internal energy, right? So I hope you guys are familiar with the concept of heat capacities, the capacity of heat capacities. So let's take a look. So delta U, your change in internal energy, is also defined as NCV delta T, right? So if I give you an example of it, if you want to look at it, what it means, if you take a box, and you fill it with some gas molecules, and then you put it like on a flame, right, and you start heating it, and what happens is that the temperature rises, the temperature is rising. So what's happening is that your molecules are gaining kinetic energy. So since they are gaining kinetic energy, definitely there is a change in the internal energy. But how am I supposed to calculate that change in internal energy? So if I were to calculate this change in internal energy, then I can say that, you know uh, I would take the uh, energy which is required to increase the right. All right, let me write it that this way. So I would take a parameter. I would take a parameter which defines that how much energy, let's say I call it as C, right? So how much energy is required, delta Q, to increase the temperature by 1 degree or 1 Kelvin, right? How much? So this parameter is called as my heat capacity. This parameter is my heat capacity. And this parameter shows my temperature difference, like this thing, the delta T shows it per unit temperature, right? How much heat you need to raise the temperature of a gas per unit, right, by 1 Kelvin, right? And but you can see there is a loophole in this parameter, because if you have a 1 kg water, it would need some different amount of heat, and if you have a 100 kg water, it will need some different amount of heat, right? Let's say take Q1, it take Q2, right? And obviously Q2 is greater than Q1. So let's put one more thing here. Let's say I define it as a specific heat capacity, which is like delta Q M delta T. Now this specific heat capacity is not just about like how much heat I need to give to raise the temperature by 1 Kelvin, but this is also about how much heat I need to give to the system to raise the temperature by 1 Kelvin of 1 kg mass, right? But in case of gases, if I take the gases, because gases are our favorite thermodynamic systems to study, because rest of the things like solids and liquids are complex to study. So but in case of gases, I can't take up I can't take up mass, as a criteria, because mass is a kind of thing for a liquid or a solid. So for gases, I can't take up mass, right? So what is my next measure? So what I will do is, for gases, there is one quantity which we have moles of gases. Is a very favorite, is a very favorite measure of ours. Whenever you want to quantify a gas, quantify gas, we normally take up moles, right? So I will define my quantity in moles, right? All right, now let small c be the parameter, and I define it as equals to uh, delta q upon mu times delta t, right? So this is my molar specific heat capacity. Molar specific heat capacity. Right, now there is one thing actually about this very special about it, that molar specific heat capacity can be defined like in two ways. And one is at constant volume and other is at constant pressure. So let's take a look at it. So what happens is that suppose you have a box, right? It has no piston, and you have this gas molecule spread out in here and like everything. So what you do is you provide it heat, just provide it heat, and the temperature of the system goes up, and the kinetic energy of the particle increase. Actually, kinetic energy of the particle increase. That's why the temperature goes up, right? So, and you will apply some heat, delta Q, and some raise in temperature being delta T. So I can define my and all this thing is happening as a constant volume. So I will write it as delta Q V, right? So I write it as CV equals to delta Q V upon delta T times mu, right? Mu is the amount of gas in the box. Now here is the thing: since you are increasing your temperature, but your volume is constant. Your volume is constant. So if you remember my gas equation, that is PV equals to mu RT. So this all thing is constant, so it's like P is directly proportional to T. So you are increasing your temperature, your pressure will also increase. So if you are making your volume constant, you can't have your pressure constant, right? So you have to keep that in mind, right? In the same way, so if I take my pressure constant, if I make my pressure constant, again it's PV equals to mu time RT, right? So if I make my this pressure constant, I can't have my volume constant, right? So it means that the vessel I'm going to consider, it need to have a piston, right? It need to have a piston. So when I will give it a heat, when I will give it heat, so what happens is that the gas molecules inside will actually gain kinetic energy and will start moving here and there, and they will apply a force on this piston, right? And it will eventually do some work, right? So what happens is that the delta Q P heat that you have applied increase the temperature of the gas by some delta T, right? So I call this parameter as Cp, right? So delta Qp upon delta T divided by mu, right? So here is the thing, that your Cp is always is greater than Cv, because what happens is that this heat that you have applied not only goes into increasing the temperature, but also goes into work. So you need to take care of that, right? So the heat that QP not only includes the heat that is required to raise the temperature by 1 Kelvin, but also includes the amount of work it has done over it, right? So with this, we have cleared our concept of CP and CV. Now let's look at it why I talk about CP and CV, right? So we talked about that in internal energy, I just care about how much the kinetic energy or potential energy of the particle has increased, right? And in case of ideal gas, which will be considered throughout the course, we only care about how much kinetic energy of the system has increased, right? So I can write it as, because in CV, I'm only taking care about the heat that changed my kinetic energy of the particle. I mean temperature, because temperature is actually the measure of the kinetic energy. So my internal energy can be written as delta U equals to mu CV delta T. And if you look at this equation carefully, this thing is actually equals to the heat at the constant volume, right? Now the thing is, if I write this equation, delta U equals to uh, delta Q minus of W. So I can write it as delta Q equals to delta U plus W. So now let's take this heat into account. So I want to calculate a heat at constant pressure. So, heat at constant pressure, the amount of heat required for a certain, like, to given to a certain system or given out by a certain system at constant pressure. So let me write it as delta QP. It could be simply written as delta U plus like delta of PV. Now I know that my pressure is constant, so I'm just simply going to take my pressure out. So this is delta U plus P delta V. Now this thing of heat at constant pressure is my new like state variable called as enthalpy, denoted by delta H. So this is my enthalpy. So enthalpy is nothing but it is a special kind of, it's a special kind of energy, or like, energy can be in any form, so I just call it as heat. It is a special kind of heat. So whenever I say I'm talking about enthalpy in a reaction, or enthalpy of combustion, it means that I'm talking about that my system is at constant pressure. And for normal cases it is 1 atm, but it could be like mm, changed through the laboratory conditions. There is no problem in that. So I define my delta H, that is enthalpy, equals to delta U plus P delta V. So with this, I hope your concept is cleared. Thank you for watching the video.